Hello everyone, it's April the 8th. Alright, so first things first, we're going to do today's challenge, which is an easy problem, so thank you very much. And then we're going to keep working on the 2226 that we got TLE yesterday and try to see if we can figure out a new way to handle this. Not quite sure, but I'll get to it. I'll get to it. Yeah, this is still problematic. Very, very problematic. Okay, so let's first check. Kth largest element in a stream. Design a class to find the kth largest element in a stream. Note that it is the kth largest element in the sorted order, not the kth distinct element. Implement this initializes the object with the integer k and stream of integers nums. Add appends the integer val to the stream and then returns the element representing the kth largest element in the stream. So if we have 3 nums as a stream, and we add 3, add 5, add 10, add 9, and 4, and 1 is the third largest. So we start from 2, 4, 5. We add a 3, short term 4. With a hash into 5. 10 doesn't affect. 9, okay. Most TensorFlow call guarantee that there will be at least k elements in the array when you search for the kth element. Now, we can solve this using sorted list. So sorted list allows old log-n performance when you append value. So we just append, add a value, and then check for that. So that would be the easiest way to handle. But apparently, we don't want that. We're trying to do it ourselves. And how do we do this? The numbers are pretty big. Oh, that's a no-go. So every time we push a value in, and we want to find the kth largest element. Kth largest element in the sorted order. So let's see. Now let me go through the example again. 2, we sorted 4, 5, and 8. So we add 3. I return 4. We add. Okay, we add 5. Oh, okay, largest is from right to left, my bad. We add 5, return 5. We add 8, still return 5. Now we add 10, still return 5. We add 9, return 8. We add 4, return 8, okay? I think about we can make a heap out of this. 2 heaps, right? So we sort original one, and then we find a k largest, they produce a heap. We're gonna call that a mean heap, okay? And then the remaining will be the max heap. Okay, so we have a max heap from index from 0 to k minus 1. Wait, hold on. No, 0 to minus k. Yeah, doesn't matter. From 0 to minus k, right? 0 to minus k, that's the maximum heap. So every one to turn to negative. And then we get a min heap from k all the way to the end, right? So we have a min heap. So the kth largest is the min heap, right? So we add a value. So we need to check the front of the min heap and check the back of the max heap. I mean, check the top of the min heap and top of the max heap. If the new input value is smaller than the max heap, then we just push into the max heap, we return the top of the main heap, we're done. If the value is larger than the top of the main heap, we're gonna pop, right? We're gonna pop the top of the main heap, add a new one, and push that into. Okay, so that is how I'm gonna do it. I think I've done this before, and feel like this too. Hold on, I did. Oopsie doozy, I forgot to commit yesterday. Alright, I want to do it today. Man, this one is not supposed to be easy. I would say this one is medium. I would put this one to medium, because we need two heaps. So import heap queue. Okay. So initializing, and this is what we're not going to test. So what we're going to do is min heap equals nums k towards the end. No, minus k towards the end. And the max heap equals a for n in nums 2 minus k, right? And then we do minus n, that's the max heap. And then heap q dot heapify min h, and heap q dot heapify max h. All right, so that's the start. Now we're gonna add. So to check, we say if value is smaller, what if it's equal to? Smaller or equal to the main heap 0, right? Then we're gonna push into the max heap. Then we simply say heap q dot heap push max heap minus val, right? Just push into the max heap. And else if value, then we're gonna say heap q dot heap push the max heap, or push heap q dot heap pop main heap with negative value here. Ooh, hold on. I just realized something. So a new value comes in. So what we guarantee is after this, everything is in order, right? So the new value comes in, and hold on. So the max heap will have something the largest. It must be smaller than the main heap, the smallest, right? So a new value comes in. If it's smaller or equal to this, and we say we push into the max heap and everything remain in order. If it's larger than this, right? If it's larger than this, then we pop this, push into this, and just replace with it, right? We just replace with it. And if it's smaller, yeah, Yeah, I think that's right. So max heap push min heap. Pop it out, right? And then heap q dot heap push main heap value. Now we return always main heap the front. Let's see. Main h. Oh, jeez. It should be self. My bad. I forgot. Well, here, and here. All right, run it again. Jeez, come on, man. Wait, one more? Any more? All right, I think that should be it. Come on, man. That ain't right. Expected 4, I got 3. Oh, I didn't sort. The nums dot sort. Forgot to sort it at the beginning. Alright, I think this one should be right. No problem. Runtime error. What? Oh, shoot. That is correct. Ah. Holy guacamole. So if yeah, because we need to pop from the main heap. What if we don't have main heap? That's right. Hold on. And num's length can be 0, but it's a guarantee there'll be at least k elements in the array. So k is 1, so it won't be empty array, but it is possible, right? Wait, how would that be possible? That main h is empty. Oh, you're given an empty array. Wait, hold on. I clicked the wrong button. There will be at least k elements in the array when you search for. So when you search for, maybe we'll change the order. Maybe we should add it first. But add it where? We don't know where to add. So I do have to examine, like, if there's nothing in the main heap. We never pop from the max heap, right? We only pop from the main heap. So if there's nothing in the main heap, right? What if there's nothing in the main heap? there's nothing in the main heap that we compare to the max heap, right? And if the max heap has to be larger than the max heap, what if it's equal to? Darn. Let me think again. Oh, that is a good test case. We can have empty at the beginning. Okay, so if main heap is empty, that's not possible because guaranteed that they're during. So the only possibility is main heap. I just need to add one value in the main heap and then one value in the max heap as well. All right, so the main heap we need to add the largest value, and the max heap we need to add the smallest. No, on the max heap we add a large value. So the large value, so it's going to be a max heap, and then so the negative will popping out. So this is to prevent this thing from going. So okay, so what we're gonna do is import math, and then we simply just say self.min this.append math.infinite, and this one also, right? This one's fine. I don't need to. So just this is in case main h is empty at the beginning. All right, so now this one shall work. Wow, I kept just pushing Control C. That should be Control V. All right, so let's try this. This is a good test case. It's a very good test case. This one should be right. We always have something. What? Inf. How? The value is smaller than as infinity. So we shall hold on. Oh, if it's smaller than this, then we go here. So that should be pushing the negative. Negative infinity. So it's a very small value. But if it's a very small value, then if it's a small value, then we'll pop this small value. All right, we'll pop this small value and push it into here, and I will push the current value into it. So min heap is right. How about the max heap? Well, the max heap, this one will be at the top. So this one will always be at the top, if you think about it, right? Because it's a minus infinity. So this is the smallest will always at the top. And we do have to do this. Oh, hold on. I push in the minus vowel. No. It's smaller than this is not true. So we're gonna push the pop, which is minus infinity, and this would be plus infinity. Oh, this shall be right. So now we push a plus infinity to the max heap. Oh shoot. Well, the first one is wrong. The second one is right. Huh. How? It only works if, you know what? We need to handle this. This is not gonna work. We need to handle the case when min is empty. So what do we do if the main heap is empty? Well, if main heap is empty, right, and it will only happen at the beginning, in the first round, because later on it's guaranteed that it will not be empty, which is true, right? Which is true. So it will only be empty for one round. So we just say, if it's empty, we just push it in. That's it, right? So okay, I just say if not self.min this, and then we just push it in. All right, we just push it in. All right, else, then we do this. Yeah, it's easier to resolve this issue. There we go. This one shall be right. Come on. Show some love. Oh, holy guacamole. Alright, we got another wrong. Oh, I thought this was easy. Wait a minute. What happened here? Output expected. Okay, this is not right. So initial value is 0. Okay? And when you go 2. So the first value pushing in is -1. Oh, it's the same problem that you didn't fill. So -1 coming in, and so -1 is smaller, but we haven't filled it. So no, it's not this. If len this is smaller than k, then we just push this in. Self.k. Wow, this problem is good. It's quite tough. All right, third time. Third time should be a charm. Madre mia, this is not expected. Oh, that's pretty hard. $703. It is labeled as easy. It is quite challenging. I know it is a heap problem, but I got stuck. I got a few errors because I didn't fully realize, right, the edge cases where k is larger than len self.min. So when that happens, right, so when that happens, which means there are not enough values in min heap to generate the kth largest value, we simply push new numbers into main heap. So O log n, right? So O log n per operation. This is not easy at all. Yeah. Result is heap. Oh. Yeah, I was actually thinking, why you need to keep two heap? We just need the k largest. My bad. Yeah, that's what we should keep all the values. But it's a stream, so I don't know. And log in for initialization. Okay, so so my solution keeps all the values. Yeah, let's write the other solution. So this is the official solution. It does not keep all the values, but only the k, the top k, right? Top k numbers. Go ahead and sort, and we can just say, oh, just get self.heap equals nums. Right? Yeah, we don't. Oh, we sorted. We just. Oh, we sorted. We don't even need a heap file. So we already sorted. All right. Well, we already sorted it, so we don't need a heap file. So we sort, get heap, get k. And that's it. And then add if, and then do this. We can pop, right? If it's smaller than k, we do this, and then we say while we always. Wait, hold on. Yeah, we can do this. We always add, and then we just push it out. I mean, we can make it. Yeah, we do this if, and then we push, and then we say if val is smaller or equal to self.heap. These are not main heap, they're just heap. Alright. So if it's smaller than self.heap 0, if it's larger than, alright, then we need to heap q.heap push pop. I remember self.heap and a value, and then return this. Let's try this. So we want to keep k. Yeah, that's on the right. Simpler. Ooh, it's not right. The heck? Wait. Oh, Aleph. I don't know. Today was not good. Easy question. This took so long. So many tries. It's Aleph. Alright. That's it. That's it. That's it. Alright. Let's back to this. So we got stuck yesterday. And this solution failed these two. This one will get out, right? Low or high. And low is always larger. So we can always try low, right? If low works, then low. Otherwise, we return high. So low will be the larger one. High will be the smaller one. Wait, hold on. Let me see, what's low and high? Low and high, smaller one. Low and high. Ah, high is this. Low, high, low, high. Low and high. Low and high. So basically, if low works and we're low, otherwise we do high. But we have to check high as well, right? If high doesn't work, then need to be high minus 1. I'm guessing. But the thing is, we could, like if it's 4, right? If it's 4, we can go 2, 2, and 2, 2, right? So 2, 2, 2, 2, that's 4. But 5, right? We say we want 5. It only be 1. Because 2, 2, 2, 2 cannot be 2, so it has to be 1. And that one will fail as well. The result will be 3. So the problem is not minus 1. The problem is when we come out, right? If a low doesn't work, then we're going to check high. And if high works, then we'll return. If high doesn't work, so basically, we can do high as well. So we're going to do this. So we're going to do this. All right, so 2 more times. And return high. If neither works, right? If neither works, then what? If neither works, I don't feel right. I don't think this one is making it any easier. I have to check these two, right? And then if neither works, then we have to say for res in range, total divided by k, total divided by k. Right, if index is be res is so stupid, so convoluted. Oh. If not res. I don't think this one's any faster than what we have yesterday. Because yesterday we not able to solve. No, this is not gonna work. No, I think it's still TLE. Oh, yeah, runtime error. Division 0. Oopsie doozy. Or still timeout. Most likely. Did we improve at least? I think yesterday was only 30 something. I've improved to 40 something, but that's still bad. All right, so that's not the way to go. I gotta see the hints. Hint 1. I use this, but apparently that's not good. Enjoy. What's hint 2? Isn't this what I'm doing? This is exactly what I'm doing. Maybe these binary searches making it worse? I mean, I can just from the large to go k times. What at most k times. If you add up to k, then we're good, right? Let me think. So we add up, so we keep from the top. We keep adding once it's larger equal to k, right? And if we keep adding, it's smaller than k. I don't know, man. Yeah, the thing is, if it's in between, we can find it. But if it's not in between, 0. Oh my god. We just start with 0. If we start with 0, then we are guaranteed to find one. And eventually, high don't is low is good, or mid plus 1. So I think we'll return low minus 1. Division by 0. Division by 0. How about we go low is 1? Hold on, low is 0. So if mid is 0, right, that we definitely cannot do. So we say if not mid, or well, almost this one. Answer is 10. So low is 10. Oh yeah, low get to high. Hold on. So what happens is the low is 9, right? And then plus 1. So mid plus 1 has never been checked. So I think we just do one more time. Okay? Just low coming out. If not low or low larger than equal k, then we just turn low. Otherwise, return low minus 1. Then we satisfy everyone here. My dumb bot can't figure out. Oh, that's much faster. Yep. It's not that hard. It's not that hard. I think it's just I was stuck on the idea that I need to use the smallest value as my lower bound. Who said so? Like, seriously, who said so? We can set to 0. I don't understand why I did not realize that. Yeah, so I was correct. I was correct to use binary search for this problem. The where I got stuck was that I was using the smallest value in candies as the lower bound. Now this is not right. In fact, we shouldn't even be using this. This should be total divided by n. Huh? So total divided by n is 6? That doesn't make any sense. That should be the maximum you can do, right? Hold on. 6. Oh, it's not candies. My bad. K. Yeah. This is wrong. Lower bound should be 0. And a higher bound should be total number of candies divided by K. Yeah. The one tricky part is that after the binary search, right, is over, we have to check low one more time. I have to check low one more time to make sure that one more time, because the loop search ends with low incremented by 1, right? And the new low has never been checked. It is possible that the new low can satisfy requirement as well. Owen login. I bet this is even faster. Yeah, actually I'm not sure, but run this just to everything's in check. Try that. I hope this one's faster, because the higher bound is lower. About the same. About the same. 1336. 87. Alright, so this one's done. But I feel very dumb. Binary search. Oh, they did +1. No, that's just to get 0 in the right. It's a giant number. Keep left does not change. It's just a little bit thing to keep in mind. Oh, binary search problem. So I do left smaller than right. And that's what I do as well. I'm going to do left plus right plus 1 divided by 2. And then move right to small. So we know the left definitely is good. I think on this you can avoid the issue of this becomes 0. Mid becomes 0. So mid will never be 0. So mid is always biased a little bit. It's a little bit larger. So the mid is biased to a little bit to the larger one. So we set left to the mid, which is a little bit larger. What's the reasoning? Never bother thinking anymore. I like left smaller than right. To find the first element valid, find the last element valid. The last element valid. We want the larger one. If we want to find a maximum, we use this. If we want to find a minimum, we use this because that's the first valid element. That's the last valid element. Okay. So the proposal by Lee. So this is a solution by Lee 215. Sort this and this, which is fine. I mean, what I just realized is that we can just do sum divided by k. We don't even need this, right? So mid plus 1, and we say if right for C in Candice is larger than or equal to k, right? Then we say low equals mid plus 1, else high equals mid. Let's say return low minus 1. What's going to happen? Oof. So when we do this, because mid, I already biased to the right. So we don't want to bias low anymore. Alright? So we don't bias mid, low, but we push in this one. And then return low. Index out of range. Of course index out of range, because it's supposed to be C. According to Lee 215, this is to find the last valid element. I say since mid is already biased, is already biased to the right. We don't bias low anymore. Yeah, because initially it's biased to the left, right? It's biased to the left, and then we should not bias twice. So it's a low plus equal one. But now mid is biased to the right, so high need to be. This is the important distinction. Yeah, so to me, right, the most important part is the two different techniques for binary search. We add one here, then we do -1, which is handle the last element. This is what we want, the last element, which is the largest. We can also search for the smallest, right? The smallest. Then it's going to be, then we shall return low as well. Well, the smallest will actually just be first element that satisfy. Shouldn't they all be 0? Actually, I'm curious. What if we do this? Nope. It doesn't make any sense. If we do this, it doesn't make any sense. Interesting. If you do this, it doesn't make any sense. Try to find the first element that makes sense. Oh, we try to find the last element that makes sense. Wait, what are you saying? Like, I don't know. Nah, this gives me. This is like magic, right? Yeah, this is like magic. But does this work for all binary search? Honestly, I think Yeah, either do this or do the other way. Just do the other way when you come out, because low is low plus one, mid plus one for it to come out. So what's gonna happen is low might be pushing too hard, so you have to check, right? That's the difference. And this one, because low doesn't change, and a high goes, right? So high goes because it's bad, so high goes. Yeah, makes sense. All right, that would be that, and we're gonna shut it down today. Huh. The first one's quite hard. The easy one. All right, I'll see you guys tomorrow for the contest as well. Adios.